Assalamualaikum warahmatullahi wabarakatuh, and good evening. We will continue our class today after we have learned about the previous power plants that I have told you previously. Okay, today class, what I would like to talk is about the modifications that can be made for the uh, Brayton cycle. So let's jump straight over to the Brayton cycle. As you all know that the modifications of the Brayton cycle can be modified with by doing some uh, coupling, by doing some modified on regeneration, putting intercooling, and also put another method called reheat. Okay, but today we only will discuss based on the modifications by regeneration. Okay, let me share the file or the slide that we will be look on. Okay, the Brayton cycle with regenerations. If you all see, this is the pictures schematics diagram of the power engines, power, power turbine engines. Okay, uh, basically the power turbine engines uh, have the compressor or the multi stages of compressors, combustion chamber, turbines, or the stages of turbines. Okay, and the turbines also connected to compressor. Okay, when we want to make the modifications with regenerations, that means we put some device that's called heat exchanger as a generator after the turbine. Okay. The temperature, that means the temperature of the exhaust gas leaving the temperature is often considerable higher than the temperature of air leaving the compressor. So by this concept, we can take it as the advantage. That means we put the heat exchanger or a counter flow heat exchanger, that's called regenerator, or even it is also called known as a recuperator. That means what happened there, the high pressure air leaving the compressor by the high pressure air leaving the compressor can be heated by the hot exhaust gases in the heat exchanger. That means a simple words that the hot air or the hot produced gas that come out from the turbine uh, we take it as an advantage and transfer this hot air into the fresh air after this air comes from the compressor. So from here, what happened? Heat has been transferred to the cool air, and this will make or this will result of the regenerations where since less fuel is used for the same work outputs. That means the cool air, if if the system is do not have the regenerator, that means we just put the cool air in the combustions, and maybe or example, the air needs some amount of fuels to be heated or mixed with the air. But if we make it the cool air more heated, or we heated the air, then the fuel that's in the combustion chamber will be less, because enough energy that come from the compressor mixture with the fuels here, and it will be combust in the combustion chamber. So this is the concept of the modifications with regenerations. So this is the TS diagram. So from this TS diagram, if you want, or when you want to make the analysis, so you have to draw the TS diagram like this, where in this diagram you can see it have 1, 2, 3, 4, 5, and 6 processes. So process number 1, that means from state number 1 to state number 2, this is called compressions process, or by isentropics. Process 3 and 4, this is um, expansions or power process. This is in the turbine. And 3 and 5, or 5 prime, this is combustion chamber, where the heat is added in the system. And this is a generation. Okay, generations, that means, what's mean by this generation, that means the hot air come from the turbine, then it will transfer back to the uh, inlet of the air to the combustion chamber. So the air will be heated by itself and then come to the combustion chamber. Okay, that is a method concept of how this Brayton cycle work with regenerations. Okay, we go for next slide. Okay, when we talk about regeneration or regenerator or heat exchanger, put it in the Brayton cycle, one term that we have to know in this uh, analysis is you have to know how to calculate the effectiveness of this heat exchanger. Okay, the effectiveness of this regenerations modifications is based on the symbol sin region. Okay, what is the regenerator effectiveness? Okay, actually based on this TS diagram, uh, if we see in here a graph, in this graph, what happened? Uh, Heat regenerate actual, that means come from the formula enthalpy 5 minus enthalpy 2. That means 0.5 minus 0.2. This is generation heat generation actual. Heat generation maximum when point number 5 is become point number 5 prime. Okay, if phi is equals to 5 prime, that means the generation or the effectiveness is 100%. But if phi and 5 prime is not in same point, that means it may be 80%, 70%, and so on. So generation regenerations maximum is H prime minus H2. That means H prime minus H2, and it's also equal to H4 minus H2. Okay, and when we simplify these equations, what happens? We can get the formula for regenerator effectiveness. That means heat regen actual minus by heat regen maximum. Therefore, the equation will be H5 minus H2, H5 minus H2 over H4 minus H2. So this is the equations for regenerator effectiveness. But you have to remember when we talk about Brayton cycle, it uses air as a working fluid. So when it uses air as a working fluid, and the assumption that you have to make this analysis is air assumptions. So you have to simplify or turn this enthalpy to become temperature. So you know the enthalpy formula delta H is equals to Cp delta T. So put on that equations Cp delta T in the delta H equations, and lastly these equations will become T phi minus T2 over T4 over T2. How about Cp? Cp can be neglected, or Cp can be moved because upper Cp is equals to lower Cp. So you can terminate this Cp value. Okay, and then from this equation, you also can derive to make it more complicated equations, and it will become like this. Okay, this equation is same as you derive, you make the derivations for uh, Otto cycle. Okay, here we go. Next slide. Okay, this is the theoreticals of the efficiency, Brayton efficiency with regenerations and without regenerations versus pressure ratio. Okay, as you see in this graph, the thermal efficiency actually depends on the ratio of the minimum to maximum temperature as well as the pressure ratio. Okay, it is also seen in this graph that the regeneration is most effective at low pressure ratio and low minimum to maximum pressure ratio. Okay, so this is a most effective uh, uh, thermal efficiency of Brayton cycle at uh, low pressure ratio, and also at low minimum uh, to maximum temperature. So that means you can answer, can regeneration be used at high pressure ratio? Of course, it can. But based on this theoretical and experimental has been done by researcher, so we can generate, we can modify, but the result is just as the same as without regeneration. So if you want to if you want to make the modification with regeneration, you have to make sure the pressure ratio lower and the temperature ratio minimum to maximum temperature must be lower too. So you will have the most effective thermal thermal efficiency for Brayton cycle. Okay, let's see the example problem. Okay, example problem. Okay, will on. I will show you another slide. Okay, from this slide, we try to look on the motion. Okay, air enters the compressor of a regenerative gas turbines engine at 100 kilopascal and 300 Kelvin and is compressed to 800 kilopascal. The regenerator has an effectiveness of 65% and the air enters the turbine at 1200 Kelvin. For a compressor efficiency of 75% and a turbine efficiency of 86%, determine the heat transfer in the generator, the back work ratio, and also the cycle thermal efficiency. So to solve this problem, firstly you have to know that these cases come from the Brayton cycle, because this is generation gas turbine engines. So it uses air as a working fluid. So the method for the calculation analysis is must based on the calculations formula, not based on the what you call uh, steam tables analysis. Okay, based on the formula. Okay, so here we assume air as an ideal gas with standard specific heat, and also we use cool air as assumptions. Okay, this is the diagram, TS diagram, that can be plotted to get or to make it more simple to understand the questions. So we have 6 processes here, and compressor and turbine is between two pressure. That means 800 kilopascal and also 100 kilopascal. Okay, from there, firstly, we use a compressor analysis. Okay, the isentropic efficiency at compressor exit is okay, because the compressor we assume as the isentropic, so we can use this equation, the equations that related between temperature ratio and pressure ratio. So using these equations, you will get the T2S. That means for ideal. Why I use T2S? Because in this compressor, it also gives the uh, efficiency of the compressor. So if the question, or if you know the efficiency of the compressor, that means you have to find the actual value for the temperature. So the ideal temperature is after you put in the equations, you will get like this, 543.4 Kelvin. And then use the formula of the compressor efficiency, where we got a W isentropic compressor over W theoretical for compressor over W actual. So put the equations in the temperature, delta temperature, because this is air, so you cannot use you cannot use properties tables. You just use the formula, so you find temperature here. From this equation, you will get T2A, that's my actual temperature. So after putting all the values in this equation, you will get 6 to 4.6 Kelvin. This is the temperature, actual temperature for the compressor at state number 2. Okay, seeing the compressor is adiabatic and has steady flow. So you find the compressor work based on H2A minus H1. We use H2A. Okay, and then simplify delta H enthalpy formula to become Cp delta T. So put all the value, the temperature for actual minus temperature initials, and then we will get the compressor work. Okay. Okay, we go for the turbine analysis. For the turbine analysis, you also have to do like the previous one for like the compressor, because again in the question it say this it have a efficiency for the turbine. So you have to find the actual value for the turbine. So using the this is turbine work formula. Okay, uh, m dot cp delta t. I use temperature actual, okay, for these calculations. So in here, because turbine, we also assume as an isentropic, use the isentropic equations relationship. So from here, you will get T4 ideal is 662.5 Kelvin, and then as same as a compressor, the efficiency for turbine can is being if given. So use the equations, use the formula for efficiency turbine. So put all the equations, and then from there you will get the actual temperature, 737.7 Kelvin. Okay, and then find work for the turbine. Use the work for the turbine H3 minus H4, and then change it to delta T. So put in all the value, and then you will get 464.6 kilojoule per kg. Okay, per kg. And the bad work ratio, just only remember the equations. Bad work ratio is work in over work out. So work in is work compressor, because compressor, we know we need the input to the compressor. Work out is work turbine. So because turbine produce work, so it will work out. So put all the value, we will get 0.7. This is bad work ratio. And then, so this is generation analysis. Okay. In this generation analysis, in the question, it gives the effectiveness of the regenerator. Okay, we know the value of effectiveness of that regenerator, and also we know the formula there. So from this formula, you find T5. Okay, because T5 is needed to use in the calculation afterward. So from here, put all the value that you got from the previous calculations. So you will get T5 is 698.1 Kelvin. Okay, and then from there, T5, uh, T3, T3. I think we have find T3 from here. T3 have been given. So from there, we want to find the heat input to the system. So Cp delta T minus T5 here. So put all the value, and then you will get Q in, okay, in term of the unit kilojoule per kg. So the thermal efficiency for this Brayton cycle is using this formula, basic formula, W net over Q in. So you have to find W net. Okay, W net come from the formula W turbine minus work compressor. So put all the value, we will get the answer for the W net, work net. So using that value for work net and Q in, and lastly, the Brayton cycle efficiency, thermal efficiency is 27.4%. Okay. Okay. So I think uh, I think that's all for today. Uh, if you got any answer, you can just WhatsApp to me, or just email to me, or just communicate to me and tell what is your problem. We can discuss. Okay, this all for today. Uh, See you later in the next class. Okay. Assalamualaikum warahmatullahi wabarakatuh. And have a nice day.